Hey everyone, it's Tony here. Today I'm going to walk you through creating a simple arrhythmia detector using TensorFlow Lite Micro, and we're going to deploy it on a Arduino Nano. It's a very simple project that we can perhaps wrap around in just one afternoon, and I will put all the code I use in this video in the description below, so you can follow along. So before we begin, we will need a few things. Of course, you will need a computer. I'm using a MacBook, but I think this works on a Windows PC as well. Second, you will need a microcontroller that have TensorFlow Lite Micro support. One such microcontroller is the Arduino Nano 33 BLE Sense, and is what I'm going to use in this tutorial. But as you can see, this one is sold out. So instead, you can also purchase the Arduino TinyML kit. As you can see, the Nano actually comes with pin in this kit. They also have a dedicated camera module that have TinyML support. We will also need a ECG sensor. I am using the SparkFun AD8232 sensor board in this project. Of course, for that to work, you will need some electrode, some cables, a breadboard, and some jumper wires too. Also, I want to be clear, I'm not a medical professional, and this is by no means a medical device. So please consider this as a cool way to dip your toes into machine learning with Arduino, and please don't rely on this for any medical diagnostics. So here's how we're gonna do this. First, we're gonna grab some ECG data from the MIT-BIH Arrhythmia database. Then we're gonna train a model on Google Colab with TensorFlow, and we're gonna convert this model into a TensorFlow Lite Micro compatible format. Third, we're gonna do some C++ programming. We will focus on writing classes that allows us to do peak detection in real time. And fourth, we're gonna write some unit tests and run them on our local machine. This step is totally optional, but I think it's always great to validate our model and algorithm before we moving on and deploy it on Arduino. And lastly, we are going to put all pieces together and deploy the model to the Arduino. And so let's begin part one. Let's begin by visiting the MIT-BIH Arrhythmia database website. We can scroll all the way down to the file section and select download the zip file. And this will download a zip file that contains the ECG recording and annotation that we need for this project. The website also comes with this waveform viewer. If you click on this, it will open a viewer that allows you to visualize all the record contained in this database. So after downloading, unzip the file, and maybe I should create a directory named data in this directory. By the way, please ignore all these other things. You don't need this for this project to work. And you can just drop the database file that you just unzipped into this folder here. So I call my project directory Tiny Rhythm Analyzer, and I just drop in the MIT-BIH database directory. You will notice several files. The .dit files hold the ECG signal, and the .hea file are the header information of the recording, and the .atr files, they contain the annotation, and I think the .xws are for the waveform viewer. We don't really care about that. And also, we just scroll all the way down. Take a look at the MIT-DB-dir folder, and if we click on this, this is actually opens sort of information guide to the database. You will find details about the database structure and annotation. I think I will pay particular attention to symbol use in plot, and this will tell you the meaning behind the annotation code. For example, N is for normal beat, and V is for premature ventricular contraction. Let's go back. I will also pay particular attention to table of beat types. It provides a count of each type of annotation across the records. So now it's step 2, that's train a model on Google Colab. So let's start by creating a new folder in Google Drive. I'll call my Tiny Rhythm Analyzer, and within that folder, let's open a new Colab notebook. And you can rename this notebook to be something meaningful. Let's call it train model. So I here added some code to import the libraries that we need. Some of them you might already know, like NumPy, Scikit-learn, TensorFlow. Those are common. Some might be new to you, like the WFDB, which stands for Waveform Database. It is useful. Actually, it is needed to read the ECG signal contained in the MIT-BIH database. And sorry, the Imbalanced learn, it's a library that handles imbalanced data set by resampling them. Here, let's run them. Initially, it might take a while for it to connect to a kernel. And the next thing we want to do is to have this notebook be able to access the ECG data that we just downloaded. So what you want to do is go back to your Google Drive folder and upload the MIT-BIH database. And this might take a while, so let's go back to our notebook now. And here, another thing we need to do, so here I add this code. It's another thing we need to do is to mount the Google Drive on this notebook, and so that it can access whatever files that we have on the Google Drive. And remember to change this path to match the one on your Google Drive. And now we can run this code, and a window might pop up like this. And remember to click agree on everything. I'm just gonna fast forward. And so once the Google Drive is mounted and make sure that all the files from the MIT-BIH database are uploaded, it's time to visualize our data, do some data exploration. We are going to use the waveform database library to read the ECG signal and its associated annotation. And I have added some code over here to read record 100 up to the 3000th sample, and let's run this code. And as you can see, the waveform are being plotted right here. So this looks like a pretty normal ECG signal. We can, change a variable here to another record. For example, record 119. Let's see. Now, it doesn't really take an expert to see something is wrong with this ECG record. It's not really rhythmic as the previous one. So let's go back to our MIT-BIH and open the waveform viewer and go to record 119. And you will see the same signal being plotted right here. And you can see that this is the case of the premature ventricular contraction, PVCs. This is the type of arrhythmia where the ventricle contract prematurely and this disrupts the normal rhythm. In this project, we will make it our goal to detect this kind of arrhythmia with our model. And as it turns out, we need to do quite a bit of pre-processing to our ECG signal before we can feed into our model. We're going to extract the RR intervals from the signals to use them as features. If you don't know, the RR intervals is the time between two consecutive R peaks. And R peaks are the highest point in the ECG signal. And I can already anticipate some criticism of this approach. The first might come from what I call the deep learning purists. These are folks who sees neural network like a Swiss army knife. They saw it as a solution for everything. So if you got a problem, they got a neural network. And when they see this tutorial, they may ask, why not just feed the raw ECG data to your model? Deep learning is all about discovering feature from data, right? And right, I would say yes, they have a point. I believe it's certainly feasible to train a model to recognize the arrhythmia from the unprocessed ECG signal. However, with the if you take a look at the MIT-BIH database sampling rate, it's 360 hertz, and consider the sheer volume of sample needed for a model to accurately determine a beat's normality, right? How many do we need? 100, 1,000 or more? It's not really clear, and it's gonna be substantial. So this would inevitably bloat our model size and increase our inference time too. And so remember, we are going to implement this model on a microcontroller with limited capacity. So, downsampling is another option to bring down the sample size. But, if we do that, we might risk missing out some of those really sharp R peaks. And so my argument to use the RR interval is that, clinically speaking, it is an established metric for arrhythmia detection. So by encoding the ECG signal into a sequence of R interval, we have significantly compressed the data and circumvent the pitfall of overloading our model with redundant information. So moreover, we can standardize this interval to be consistent length and scale. The former is really necessary because TensorFlow model require fixed input size. The latter, which is a fixed scale, is crucial as it helps with the model tolerance to noise and signal variation. And the second type of critique would come from what I would call the standard metric proponent. These are really cautious folks who uses neural network only when absolutely necessary. So when they see this project, I imagine that they would ask, but why, uh, why not just calculate the R intervals and then use that as a feature? We can take the standard deviation of the R interval, and that may perhaps tell us how arrhythmic it is, And I believe that's a valid question too. But, in order to respond to that kind of criticism, allow me to jump ahead to some of the data that I saw when I tried this method. So right here, here's a plot that I make. The x-axis is the standard deviation of the R intervals. The y-axis here, if it's 0, then the ECG signal is normal, and if it's 1, it's arrhythmic. It's not normal. And so as you can see, although you can argue from this plot, definitely some of these arrhythmic ECG signal definitely have a more varied R interval. But see how much the overlap is, right? If we just use a single threshold to determine if a record is arrhythmic or not, then we might have a lot of false positive or false negatives. So I just think that a simple threshold model may not be really effective. And a neural network has the potential to extract more nuanced pattern within the data that a single metric might miss. And of course, please feel free to leave any criticism, critiques, feedback in the comments below. But this is what we are going to use for this tutorial. We're going to just extract 10 R intervals from the ECG signals and use them as features and feed into our model, and it will tell us whether the ECG signal that we saw is normal or arrhythmic. So hey, let's come back to our notebook, and if you scroll down, you can see that I have added a few more lines of code here, and So we're really lucky that we don't have to do any peak detection to our MIT-BIH dataset because the expert has already annotated those peak for us. And so all we have to do is to read those annotation, and we can do that by the RDANN method. And so this will give us a variable name annotation, and it comes with a couple of fields. Two of them that we care are sample and symbol. And so let's print it out and see what they are. So I print the first 10 of each, and as you can see that peaks are the sample number where the peaks are found, and the symbol tells us what kind of symbol they are. And this plus sign right here, I believe, means that this is a pacemaker peak. And so, of course, we want to filter that out from our training data. And this N here means that there is a normal peak, normal R peak that happens at sample number 135. So the goal of data preprocessing is to break up the signal into segments of 10-hour intervals and then filter them such that there are only two classes remaining. The normal class contains segments of 10 consecutive RR intervals from normal beats and annotated with the N symbol. And so these is a pretty normal beats, and I know there are only 6 intervals here, but pretend that there are 10 here. And so this signal is something that we will categorize into a normal ECG signal with a label 0. And the arrhythmic class, well, again, contains segments of 10 RR intervals. But within those 10 intervals, there are at least 2 of them will come from the beats annotated with the phi symbol, and they will be given a label 1. So let's come back to this code, and outside of for loop, let's create 2 empty lists to hold the x and y value. The x will hold the R interval, while the y will hold the label. Let's also specify our window size. Let's set it to 10. Feel free to try the other numbers. And now is to break up the interval into segments of 10. We will need a for loop, and then we will get the annotation and intervals of the current window, and then we will count the abnormal beat, and if the current window matches the criteria of one of the classes, we will append it to our list. Let's run this cell, and then here you can see how I convert them into NumPy arrays. There's one more thing that we need to address, that is data imbalance. So here you can see that I added more code here, and if we plot out the number of data, of course, belonging to each categories, and we can see that there are about twice as more normal heartbeat than the arrhythmic heartbeat, and so we will need to address that. But before that, let's split the data set into training and testing sets. We will specify 0.2 here to split the data into 80% of data for training and 20% for testing. And then here we apply SMOTE, which stands for synthetic minority oversampling technique, I think. And then we will apply it to only the training set. We don't want to apply it to the whole data set because SMOTE works by generating synthetic samples from the minority class. And so if we generate them from the testing set, we are essentially leaking information from the testing set into the training set. And then, as you can see, now the data is balanced. And so we can finally train our small TensorFlow model. I'm going to create a simple 3-layer neural network for classification. The first is a fully connected layer, aka the dense layer. Well, I have 16 neurons in it. And the second is another dense layer with only 8 neurons. And the last layer is simply a sigmoid activation layer, and it's used for binary classification. You would argue that a Conv1D neural network or a LSTM neural network might be more effective. But for the sake of simplicity, I'm just going to use this simple 3-layer neural network for this tutorial. And then let's compile the model. I am using the Adden optimizer. It's generally a good choice for a wide range of deep learning problems. I found the learning rate 0.01 to be quite a good starting point. The loss function here is a good choice for binary classifications. And then let's train the model. This will probably not take very long. So now it's finished training. Let's plot the accuracy history as well as the loss history. And as you can see here, roughly at about around the 8th epoch where we find a significant dip in the accuracy. And this kind of suggests to us that there has been some overfitting going on after this point. And validation loss here seems to suggest the same. And so I think let's take a look at the test accuracy. It's about 93. It's not too bad, but I think there might be some overfitting going on. And so I'm just going to decrease the epochs to 5 and then retrain the whole thing. And as you can see, both accuracies, both training and validation accuracy steadily increase over time, and the loss also steadily decrease over time. And the accuracy is about 92, so not too bad. But anyway, feel free to try out your own model. But what we have to do now is to convert the model into TFLite format, and we have to also hex dump it using the xxd command. So this will output it into a TensorFlow Micro compatible format. And at the end, you can find the size of this model. It's about 3428 bytes. You will find those two files here. And so that concludes step 2. And now we are up to step 3, where we can write some C++ code in Arduino IDE to create a peak detector. I prefer my code to be modular, so we will create 4 separate classes. The first class is the CircularBuffer. This is a commonly used data structure in real-time signal processing. The key is that the new data are inserted at the position of the oldest data, and so thereby saving us time by eliminating the need of shifting the whole array. And the second class is the MovingAverage class. This class is useful for removing noise, and it will use the CircularBuffer class that we just created. The third class is what I call ElasticEnvelope. This is useful for tracking moving maximum and minimum of the signal, and it's useful for peak detection where we need to define dynamic threshold that are robust over a wide range. And the fourth class is a PeakDetector. This is the key class that we will use in our Arduino sketch. It uses both the MovingAverage and the ElasticEnvelope class to identify peaks in the signal. So let's open our Arduino IDE. It will open this new sketch right here. The first thing we will do is to save it in our project directory. So I just did that, and I named this Arduino sketch Tiny Rhythm Analyzer. And so click on this, click new tab, and we will name this new file CircularBuffer.h. We're going to create a class of the same name. So remember to use pragma once to prevent multiple inclusion of the header file. The traditional pound if not def and define method also works too if you prefer that. This class will have 4 private member variable. Let's actually make this a template class. And then the first member variable is going to be the buffer itself, with a size specified by the template. So here I am going to have two integer variable here. The head is the index that points to the newest data, and the tail is the index that points to the oldest data. I also have a Boolean variable indicating if the buffer is full or not. Here I have the constructor here that sets all the private member variables. So here the push method inserts a new value into the buffer, and if the buffer is full, then the oldest data will be written, and here we also set the isFull flag accordingly. And then we will add these few methods. These should be self-explanatory. And finally, we add the square bracket operator. This allows it to access a buffer using the square bracket notation. It's a convenient way to access the data in the buffer, and we have the const version as well. The method is designed such that the index 0 always corresponds to the oldest data, and the index size of the buffer -1 returns the newest data. And this is really consistent with the behavior of probably a double-ended queue of the C++ standard library. And to perform some sort of sanity check of your code, let's go back to the sketch and then include the CircularBuffer here, save it, and then click this check mark to verify. Oh, my bad. I forgot to add the semicolon. Let's check this again. Oh, I see. Sorry, this should be a capital S, and so there's no compile time error, and in step 4 we're going to perform some unit tests on this class, so don't worry about it for now. So let's create a new file called MovingAverage. And we will create a class of the same name. And so this class is going to have two private variable. One is the CircularBuffer, and the another is the sum. You can see that the template parameter t is the type, the data that we want to store in the CircularBuffer. The s is the type of the sum variable. And so for example, if t is in regular integer, then you might want to use a long int for s to prevent overflow. And the buffer size allows to specify the window of the moving average. And so now think about how you want to implement this. So it seems a little bit inefficient if we just want to sum up the whole buffer whenever we get a new sample. If you think about this, maybe we can, instead of adding everything up to the new data, we can simply subtract the oldest data from the current sum and then add the new data to that sum. And then we can just divide the number of elements in the buffer to get the average. So this way we avoid doing a lot of unnecessary addition. So here the constructor will just initialize the sum to 0, and here the add value method is exactly what I described. So whenever we have the new data, we simply add the current value to the sum, and if the buffer is full, we then subtract the oldest data from the sum. And also don't forget to push the value into the buffer. And to get the moving average, what we want to do is we just divide the sum by the buffer size. Remember to cast it to a float variable. And this is just a getter method. And remember to make sure if this moving average class compiles correctly. So let's go back to our main sketch and include this header file and click on verify. And the sketch compiles correctly. And so we know there's no compile time error, but as I was saying, we are going to do some unit test at part 4 So we shouldn't worry about getting this 100% right for now. And so that was how to implement a MovingAverage class. And now let's get on to the ElasticEnvelope class. And so that's consider how to detect a peak. A common method involves setting a threshold like this. And if the signal crosses a threshold, we recognize that a peak has occurred, right? The key question is, what should this threshold be? So we can really rely on a fixed threshold, right? Because the signal as a whole might drift over time. Let me show you an example. It's actually happened quite often, especially on wearable devices. So if we apply a fixed threshold on this signal here, then you see it will be too tall for some of the peaks on the lower baseline, and it might be too short for some of these peaks at a higher baseline, such that we might accidentally count these P waves here. A good threshold should be dynamic, that is, it should adapt to the signal. So one approach to adapt to the signal is to monitor the maximum and minimum of the signal. The threshold can be set at the midpoint between these maximum and minimum values. However, we shouldn't retain the all-time maximum and minimum, shouldn't we? If we did, the max and min will only expand to the extreme value. So here is a plot where I track the running maximum and minimum up to a current point. As you can see, the max and min are expanding to the extreme values. So this isn't ideal, as the signal might vary over time, and in this case, the max and min just keep remaining here, and it's not adapting to the signal. So let me introduce to you to the concept that I call an elastic envelope. So the point here is pretty simple. We simply apply an exponential decay so that we pull the maximum and minimum towards the midpoint, adapt the signal over time, and see how this, operate at a decay rate of 0.01, and this is operating at a decay rate of 0.05, and you can see the envelope adapts more rapidly. And so let's go ahead and implement this concept in our code. So let's come back to our Arduino IDE, and this time we're gonna create a file named ElasticEnvelope. And we can start with the following skeleton code. We have the constructor and this method called addValue. And this addValue function will consist of 3 steps. We will update the maximum and minimum. We will also calculate the midpoint and then exponentially decay towards that midpoint. So let's go ahead and add 2 fields over here, and currently we'll initialize it to 0, but we might want to change that later. And in step 1, we basically just update the current maximum and minimum depending on the value. And then we can calculate the midpoint. And here at step 3, we apply the exponential decay towards the midpoint. Here we added a new field called decay rate and initialize it to the rate whatever the user specified. And notice that I also added explicit. It's good practice to use to make the constructor explicit if it only takes single argument. This is to prevent implicit conversion. And down here I added some getter methods, and I also want the user to be able to get the average, and so here I added a new field called average, initialize it to 0, and then set it over here. And so notice that I'm currently initializing the current min and max to 0. This is not really ideal. For example, if the value we get is always positive, then this current min will not get updated properly. And so we might need a way to initialize it. And so an easy way to handle this, to have a Boolean flag, let's name it initialized. And then we initialize it to false. And whenever we're not initialized, we will initialize the current max and min to the newest value. And then we can provide the corresponding getter method and also provide a way for the user to reset this envelope. And finally, for sanity check, let's again include the header and click on verify. And the code did compile. So we should be good on this for now. Yeah, and finally, it's time for us to implement the PeakDetector. So let's again go back to our Arduino IDE and create a PeakDetector sketch. And create a new PeakDetector header file, and we can start with this skeleton code over here. And so we want this PeakDetector to expose three methods here. So the first method, called addSample, this method takes a new sample and updates the PeakDetector. If a peak is detected, and then it will set some kind of flag to true. Then the user can call this PeakDetected method to check if the peak is detected. If so, then the user can call this clearPeak flag to clear that flag. And so here I added some new code here in the addSample method. We want to first filter the sample with the MovingAverage, and so that requires us to also include the MovingAverage header and also add a MovingAverage filter in our private member. And the second thing we need to do is to have some kind of private field that is a Boolean. We can initialize it to false, and if we detect the peak, then we can set the peak detector flag to true. And here at the bottom is where we can implement the two flag related method. I know that we're only halfway done with our ElasticEnvelope class, but before we finish the rest of the addSample method, let's go to the drawing board and address some issue regarding to threshold. So let's consider this signal over here. Let's set our threshold to be, say, this line here. And the rule is if the signal crosses the threshold twice, for example, here once and here twice, then we know a peak has occurred. But however, let's say we have this, extra spike at this peak over here, right? It's get a little bit noisy, and we might erroneously count this peak as two peaks, even though there is only one. And so to mitigate this kind of noise, we can use two strategies. So the first strategy is implementing hysteresis. And so this might sound complex, but it's just a fancy way to say we need two thresholds, an upper threshold and a lower threshold. So here we count the peak when the signal crosses the upper threshold, and we only reset this detection when the signal crosses the lower threshold. And so by having two thresholds, we effectively prevent some of the false detection in a noisy signal. Our second strategy involves defining a lower limit for the difference between the two thresholds. And so let's say the user removes the electrode at this time point. Now all we left are small amplitude noise. Since we are using the elastic envelope to estimate the threshold, eventually these two thresholds will adapt to the noise. This means that the upper and lower threshold will converge and the difference between them will be small. So if we set a minimal threshold difference, we can disregard the signal if this difference here has become too small. And so let's go back to Arduino IDE and implement these two strategies in our code. So let's come back to our code here. As you can see, I added the elastic envelope header, and I also added the envelope as a private member to this class and initialize it right here, allowing the user to specify the decay rate. And here I call the add value of the envelope to update the envelope. And then the next thing we will do is to calculate the two dynamic threshold of the envelope. So here this is the two formulas that I calculate the upper and lower thresholds. I declared over here. There is this parameter here called hysteresis. We can allow the user to specify in the constructor and initialize it over here. So when I actually deployed this code, I found out that this threshold doesn't actually work quite well. It seems to work a little bit better if we raises both threshold above the average. And so this is what I will do: 3 times here and plus 1 times here. Basically make those two thresholds above the average. And here the fourth step that we have to check if the two threshold, if it's too close to each other. If it's below this minimum threshold, then we will skip the sample here. And we can allow the user to pass in the minimum threshold diff here and then initialize it over here. Remember to declare it in the private members as well. And finally, this is our peak detection logic. So if the signal crosses above the upper threshold, we set the cross upper to true. And if it crosses below the lower threshold, then we have detected the peak. And then we will set cross upper to false. And remember, this cross upper here should be added as a member variable here too, and then we should initialize it to false. And here at the bottom, I added some getter method that will come in handy later, and also an optional reset method to clear the state of the peak detector. So once all done, let's save this and include that in our main sketch. And click on verify. And it compiles. So we finished the 4 classes here, and we should move on to part 4, where we can unit test these classes. So we have now created 4 classes for peak detection. Let's test each of them to make sure that they're working as expected. This step is optional, but I think it's a good practice to test your code on a local machine before deploying on Arduino. And personally, I think it's more natural to write code alongside with the test. So therefore, when I was actually developing this project, I write the peak detector code in parallel with the unit test. Here I'm breaking them into 2 separate steps just for clarity, but I think you should keep in mind of what unit test that you're gonna implement as you write your code. So when it comes to testing C++ code, I prefer using C++ unit Lite. It's a really lightweight library that can be easily integrated into your project folder. And trust me, it won't take more than a megabyte. So you can either clone this repository, or I will also upload this folder C++ unit Lite to the project repository. And you can take a look at these files. I prefer working with these files in Visual Studio Code, and so let's open it right now. So right here I am in Visual Studio Code, and I just open a terminal. I am in the project directory. I just have to cd into cpp unit Lite and do make. This will create a static library here, as you can see, called libcppunitLite.a that we can later use in our test. I will demonstrate how to write a few tests, and then you can write the rest of the test yourself. I will put all the code on the repository. And so in the project folder, create another directory, let's call it unit tests. And in here, add a file name, unit test peak detection. And so this file won't contain our test. Instead, I want you to paste the following content into this file. And this is the main function that will execute all the tests. We will write the test in separate files. So for now, let's create a file named test CircularBuffer.cpp, and this is a file where we will test our CircularBuffer class.
And up here, include the necessary header. And then to test the code, we just have to wrap the code with the test macro. Up here, you can specify the class name under test and the name of this test. And in here, you can just include the test code over here. Let me show you an example. So right here, I am testing the CircularBuffer class. I'm gonna call this create empty buffer, and I will construct a CircularBuffer for integer, and then at the start it should be empty and it should not be filled. So use the check macros to check the boolean, and use the check equals macro to check if two things are equal or not. Before we run a test, we have to build it. And so let's create a makefile. So here I already put the content of this makefile. You can also find this file in the repository. And the important thing to note is the include directory here. This is where the makefile will find all the header file used in the test. And so remember to reference the Tiny Rhythm Analyzer folder and the C++ Unit Lite folder. And here we're doing the same thing, and we're actually using the wildcard rules to list all the header files that is located in the Tiny Rhythm Analyzer. And down here at the library path, this is how this makefile is able to locate this .a static library. And so down here, I already cd into this unit test directory, and I can just run make, and it should compile this unit test executable, and then to run it, you go /unit test, and as you can see, it ran one test and with success. And then back to the file, you should implement more tests for the CircularBuffer and for the other classes. And that's it. That's how we perform unit tests on C++ functions and classes. So we have just tested our PeakDetector and algorithm classes. And so let's now move on to testing our model inference. First, we will head over to this TFLite Micro repository, and we should clone it. Paste it over here. And then we just clone it to somewhere on our desktop and then open it with Visual Studio Code. Ideally, we can build another static library similar to what we did with CPP Unit Lite and then use it in our project. However, I encountered some issue with my attempt, and specifically, the program had trouble allocating tensor. What I mean is, the input and output tensor were valid, all the attributes appear as null pointers. And so therefore I won't be doing that approach here. So if you know the correct way of how to incorporate TFLite Micro on a local machine, I appreciate your input in the comment section below. But for this demonstration, we're just gonna do something very simple. We're gonna overwrite the existing Hello World example in this repository and run our model there. But first, let me show you how to run the Hello World example. So let's open a terminal. Let's open a terminal here. Make sure you're at the TFLite Micro directory, and I want you to run this command here. So I wanted you to run this following command over here. And as you can see, that took a while because it needs to download some extra files and also build and run a test. This is because this is the first time we run this command. It won't always take that long, and it took that long because it was the first time you run it. And it indicates that all tests has passed. And so let's go to this Hello World example here. Go to TensorFlow, Lite, Micro, examples, and Hello World. And this is where that test was written. And so what this file does is that it defined 3 tests, each as a function. And at the bottom here, there's a main function that runs these 3 tests. And if all 3 tests pass, then it prints out all tests pass, as we can see over here in the terminal. And so what we want to do is we want to comment all these tests out for now. Comment them out. Also comment these. And then here at the bottom, we're going to add our own test. And I will include this file in the project repository as well. So the code I'm writing right here are essentially boilerplate code for TensorFlow Lite Micro. They offer a course and have published a few books on this API, which I highly recommend checking out. I will briefly explain each line as I go through them. First, we define a tensor arena. So this is essentially a memory pool where all the tensor will be allocated. We set it to be 7 bytes. You can adjust it based on your model's requirement. The align 16, this is important. This ensures that the memory is aligned for efficient access. And then we load the model. This is a very lightweight operation to map our model data into a usable data structure. It's important to ensure that the model's version matches the TensorFlite Micro schema version expected by our code. So, by the way, the model name has to match the one I've used over here. So if you haven't downloaded the model, let's go back to the Google Drive. So remember that in the Google Drive, you export the model as a TFLite and C++ format. Let's download this TFLite format for now. And then back to the Visual Studio Code, I want you to right click on this model folder under the Hello World directory. Click on Reveal in Finder. This will open a folder right here. Double click it. I want you to rename it to something else. Rename the original TFLite this N8 to something else. Let's say original TFLite. And then I want you to drop the model TFLite that we just trained and rename it like this. And rename it to be the same as the original file. And just like that, we have replaced the Hello World model with our own model. So here, as a third step, we are adding the necessary operation for our model. And because we know that for our model, it's pretty simple. We only have a dense layer, also known as fully connected layer, and each of them has ReLU activation, and the last layer has a sigmoid activation, also known as logistic activation. So we only have to add 3 operators for our model. 3 operators, so we have to pass in 3 in the template over here. Personally, I think this is a pretty smart design choice by the engineer who made this API. I think it allows us to include only the operation we need. So we don't, for example, we don't need convolution operators, so it won't be included in our final executable. So thereby we reduce a lot of memory footprint of our application. Remember that these microcontrollers have very limited memory, and so it's a waste of resource to include operation that we don't need. And then once we have all 4 elements over here, we can use them to construct a interpreter. The interpreter is responsible for running our model. And then also a very important step here is to allocate memory for the tensor. And so we call the interpreter allocate memory to allocate memory for the model's tensor within the defined tensor arena. And then we print the size of the tensor arena. And then here at the bottom, remember to return this flag over here indicating that test has passed. And here we need to call the test model function, and that's run. We can run the same command that we run before. And so it finally finished. And as you can see, the model arena size only takes up about 1 kilobyte. And so we can actually go back here and decrease our tensor arena size to 2. And let's run again, and it should still work. And as you can see, the test still passed. You may be wondering, what if I decrease the arena size to only 1 kilobyte, and it will probably give you an error. Yes, and it will say failure to allocate memory, and so it turns out we did need more. Let's change it back to 2. And here I added a few more lines of code. We will set up the input and output tensors. And so first we obtain the pointers to those input and output tensor, make sure they are not null pointers. And then we begin checking the dimension and the type of them to make sure that they match the expectation. And so we can run the test again. And so all the tests has passed. And so that was great. But now we want to actually input some test data to this model to make sure that it actually worked. So let's go back to our Colab notebook. So here we are. So the last step that we did is we exported our model and hex dump it into a CPP file. So following that, I added a few more lines of code to print out some test data that we can use in the unit test. Basically what this is that we grab 20 trials of arrhythmic intervals, and then 20 trials of normal R intervals, and then we write them into a C-style 2D array format. And so you can just copy these into the test. So here I've already copied the two-dimensional arrays that we just printed in the Colab notebook. These are 20 by 10 arrays. Each rows right here represent one trial, and all of these samples should give us a arrhythmia score hopefully greater than 0.5. And all these bottom ones are healthy intervals. Hopefully the model will look at it and output a value prediction under 0.5. And here, let's initialize these two. We want to have at least 0.8 accuracy. So if the model doesn't give us 0.8 accuracy, then the test failed. And here we will loop over the trials, and for each trials we will put in the input value into the input tensor one by one using this, and then we will run the model by calling the invoke method. And we can check if the model has failed or not. If not, and we will move on to get the predict value. And since we're iterating over the normal trials, the Y prediction should be less than 0.5, and then we will increment the number correct. And here we calculate the accuracy over here, and then print it using microprintf, and then we check if we have at least 80% correct. Here down here we basically perform the same step but for arrhythmic score, and we expect the prediction to be greater than 0.5. And so let's run this test. Yeah, and so the test passed, and the accuracy of the normal trials is about 0.8, and the arrhythmic score is about 1. And so this kind of hints at us that we can probably increase this threshold a little bit. And so let's try 0.7. Sure, and so 0.7 give us a decent accuracy in both classes, and so I guess 0.7 is the threshold that we will use. Feel free to try out different thresholds. But now that is how we can test the model on our local machine. And let's move on to part 5, where we can put everything together and deploy it on Arduino Nano. In this step, we will put everything together and deploy it on Arduino. Let's head to the Arduino IDE. If you haven't already, go to Library Manager. And search for TinyML. And download this Harvard TinyML MLX. And the next step, go to Board Manager. Search for Arduino Nano 33 BLE. And download this Arduino Embed OS Nano boards. And so in Tools here, let's select our board to be Arduino Nano 33 BLE, and we can start coding. And at the top of the sketch here, let's include all the necessary headers. And next, we will declare some global variables. To avoid name collision, it's best to place them inside an anonymous namespace. This will include the window size, which we set to 10, a PeakDetector, another CircularBuffer, and then we also have to define the tensor arena size here. Let's set it to 2 because we just found out that 2 is a pretty good number. Oh, and then we also have the error reporter, the model, and the interpreter. These are so far initialized to null pointer, and we will initialize them in the setup function. And so these are the setup code. So we need to you want to be able to communicate with the laptop, and so we need to establish serial communication at the start of the program, and so that's set the baud rate to 9600. We also want to be able to receive input signal from analog input 0, and so we have to configure it to be an input. This is actually, I believe this is not necessary, but it's just good practice to put it there. Here we initialize the error reporter. We also call the get model and then check the version. If the version and the schema matches, this is very similar to what we did on the local test. Here again, we add the necessary operators, and we initialize the interpreter. We allocate the tensor, check the dimensions, and set up the model output setting. And so let's click verify to check if the code works. Oops, sorry, let me delete this. And also, we haven't included our model. Let's head back to Google Drive and now download this model.cpp, and we will add it to our tiny rhythm analyzer. And you might need to close and reopen the Arduino IDE. Let's open it right here. Okay. As you can see, our model CPP is right here. And so let's create a header file, name it model.h, and paste the following code to this header file. Now verify, now click here to verify it again. And so, yeah, the code did compile, and so let's try to upload this to our Arduino Nano. So plug in the Arduino Nano, and it should show up in the port over here. See? And then click upload. And now open the serial monitor. Here, if we didn't get any text, then it probably indicate that we haven't got any of these error messages. So we should be fine to proceed to the loop. And sorry about that, I to add the elastic envelope here. So please put this into the global namespace here. And down here, I have added more code in the loop. And this is how we do peak detection. We first initialize a latest peak to the current milliseconds, and then we're reading one sample. We can optionally print this to the serial monitor, and then we pass this sample into the peak detector. And if the peak detector detects a peak, this flag will be raised. And by the way, remember to, at the end of this condition, remember to clear this flag, otherwise you will keep entering this condition over here. We'll get the current time and then take the difference. And this time difference will be our R interval. And so we will push this R interval into the buffer. And then we will also add this R interval into the envelope. This is mainly to keep track of the current maximum so that we can normalize the R interval later. If the buffer is full, that is, if we get all 10 data that we need, then we can run the model for inference. Here we pass in each R interval one by one to the data, and then we run the inference by calling the invoke method. Check if it has failed. If it fails, then we hold the execution here, and then we get the result from the model, and then we just print it to the terminal. And at the end, remember to clear the flag. And so that's upload this code to the Nano and see if it works. So right now, all we get is, let's look at the serial plotter. So all we get is garbage because we haven't connected anything to analog input 0. And so here I have my Arduino Nano connected to the computer and also put on the breadboard over here. And so, and here is a potentiometer. And so that just connected all three terminals. So I want these two to connect to the ground and the 3.3 volt pin respectively here. And then this should connect to analog 0, so like this. And so right here, if I rotate the potentiometer, you can see that on the screen I can mimic a sine wave. So, however, we don't have an intuitive way to understand the model's output, right? And so let's use the built-in LED on the Arduino Nano to indicate the output. We can create two files. We will call them detection responder, right? The header file here, let's create it. Let's call it detection responder.h and detection CPP. So here over here and here in detector responder.h, we will expose two functions, setup and respond to detection. Here in .cpp, we aim for the green LED to be on when the output indicates a normal sinus rhythm. That is when the output is less than 0.5. So I should actually use 0.5 here. On the other hand, we should turn on the red LED if the output is greater than 0.5 here. So this red stands for R, G stands for green, and those are macros that are included in the Arduino.h header file. And remember that these LED are active low, so you have to set it to high to turn it off. So here during the setup, we turned all of them to low. We turned all of them off, and then here we turn on the respective LED by setting them to low. And here back in the main sketch, as I did, I include the detection responder header file here. And then let's scroll all the way down to the setup function. At the end of the setup function, that's called the setup function to turn all the LED on the board off. And here, let's comment these two out. Instead of printing the prediction, that just pass the prediction to the detection responder, and it will turn on and turn off the LED correspondingly. And so that's upload this code to our Arduino. Let's hit upload. And let's check out the serial monitor here. And I will begin to simulate a heartbeat by a sine wave motion here. As you can see, yeah, it now turns green. Now if I stop, it turns red, and if I go back to normal sinus rhythm, it turns green again. If I stop, it turns red. Yeah, so that was fun. And here also, if you have one of these ECG sensor, feel free to hook it up to the Arduino and test it out yourself. And here is my heartbeat. It's pretty regular, and so the light turns green. This is expected. I happen to know that I don't have any cardiac arrhythmia, and so this is expected. But again, please do not use this as a diagnosed device. And also, when you hook it up to yourself, please avoid electrocuting yourself. Currently, I would advise people to disconnect their laptop when they do this. And right here, if I just remove one of the electrode, as you can see, I messed up the signal, and the light immediately turns red. And what would happen if I put it back on? Okay, let's wait for a second. It should turn green. Yep, that's it. And so this concludes our tutorial on creating a basic arrhythmia detector. There are several aspects that could be improved. In the Arduino sketch, sampling interval are not consistent, and so we can improve that. Additionally, it's relatively easy to mislead the model into thinking that a signal is a normal sinus rhythm using a potentiometer. So we will have to address that too to make it more robust. Also, the issue of drifting baseline remains partially addressed. Although the ElasticEnvelope's dynamic threshold provides some help, it will be helpful if we can remove the baseline of every signal. It's also important to note that the project focuses on only detecting the PVC arrhythmia, leaving out other types of arrhythmia. And also, the peak detection method may not be effective for everyone, especially for those with really prominent P or T waves that could be confused for R waves. And lastly, as I was mentioning, a 1D convolutional model or a LSTM model will probably be more suitable for time series data like this. And so that's something worth trying as well. And so anyways, I hope this project, you find this project fun and informative. Thank you for watching. If you have any feedback, suggestion, or question, please leave it in the comment. I put all the code on my GitHub repository, and I'll see you in the next video. Thank you.